Good afternoon, everybody. We are planning to have a discussion session up here entitled "The Future of Heap Leaching," and we'll see how far we get, because quite frankly, many of you in the audience will have your own thoughts about the future of heap leaching as well, and we'd very much like to hear about that. The panelists are Dan Kappes, founder and president of Kappes, Cassidy and Associates. Mark Smith, director with Pateau Associates, USA. Thom, professor emeritus.
Yes.
Emeritus, University of Nevada, Reno. Panel will be led by Mike Milczarek,
okay,
and who's the president of Geosystem Analysis. And I'll just stay here.
You get to go last.
I'll get to go last. Okay. All right. Thank you.
Okay, so just real briefly, the format that we decided upon is that each of us is going to take about 5-6 minutes to talk about some thoughts about a particular topic. And the idea is to just throw some ideas out there as to what we think is important, what we, as an industry, we should be thinking about in regards to this topic. And then after we've done those presentations, that should give us about a half hour to open up to the audience and just answer questions and start a discussion amongst us all.
The title, it took me a while, but I realized what I'm seeing, and I'm seeing everywhere, all my clients everywhere, the project is that bigger, higher, and more complex for conventional heaps, not higher for dynamic, but everything else. So we're dealing with enormous projects, which pushes our understanding of behavior and makes us be better engineers or pay a stiff price. Next slide. So in terms of more complex, next slide, please. Trying to mentally control it, but it's not working. So in terms of more complex, it's more geotechnically complex. That's my area of expertise. And one of the things it's demanding of us that I don't think we're always rising to the call is substantially better and earlier characterization of the ore. Understanding the behavior of the material, how it will age, especially if it's an acid leach environment. And the little picture down there is a spent ore disposal on the right, a spent ore disposal facility that was supposed to be a functioning dry stack. And the repios are flowing under dead weight about 1.5 kilometers, and now they're basically treating it, managing it with it's like a tailings dam at a approximately $200 million retrofit. And the dynamic heap is not as thick as they thought, and the leach cycles are vastly longer because they're running at really low irrigation rates and all those prices that would have come out of proper characterization. And part of that characterization has to be more time and effort on proper aging. So the graph on the bottom left is actually from the Escondida mine from many years ago on their bio leach, where they allowed us to run, I think that was a 500-day period, and we got the test like every 50 days. We got samples, and the original design work was done out at like the 200-day period. Doesn't represent at all large scale performance of that facility. And next slide, please. Next slide. See that brain's not working, that brain connection. Yeah. So I love as a geotechnical engineer when I get to talk about metallurgy, because I have complete permission to be entirely wrong because I'm a geotechnical engineer. But we're processing a wider range of materials. There's multiple talks this week on nickel. There's a couple of gentlemen here from Finland who have an extremely interesting nickel sulfide heap leach project. And it's not just that; it's a polymetallic nickel, zinc, copper, and cadmium, cobalt. I know Dan dabbled with a rare earth project, and I think we'll see more of that. I've been on both nitrate and iodine leaches, and I put a question on lithium because why the heck not? So, next slide, please. And we're also seeing more demanding closure. This is certainly not heap leach specific, but it absolutely affects us, more rules, more expectations, increased oversight and so forth, increasing reliance on, and this is heat specific in heat biotreatment, and less reliance on active closure. The days of just we'll pour money in a trust fund and that's that. There'll be cases where we still have to do that, but we're being asked more and more to not do that or do that less. And next slide. The flip side is there's some opportunities here. From an ESG perspective, heap leaching has some real advantages, and we can gain some benefit by recognizing that more overtly and taking public credit for it, taking credit in our community relations, but also making sure we're designing to optimize that. And these were some of the things that came to mind for me. And I know when the sustainability project was published, they actually expressly acknowledged heap leaching as a sustainable technology. So, and I'm very happy to have spent a big part of my career on that sustainable technology.
We're going to turn over to Dan. Could we get a clicker up here? And then we don't have to instruct you guys to advance the slides.
Okay. Everybody has.
I don't have any slides, so I don't need the clicker. I guess the interesting question for Mark is he's talking higher heap leaches, but as I recall, you gave a paper yesterday on a nickel laterite heap leach that's all of maybe 4 meters high.
So to clarify, you're using my own words against me?
I am, yes, that's fairly easy to do.
Yeah, it's low hanging fruit. Yeah, but we also learned yesterday about a 274 meter high heap. So there, they balance out.
So I guess in the gold industry, of course, it's a lot easier. Gold ores don't really evolve much. I think that gold ores do evolve a little bit, and that clays in gold ores tend to react with the alkaline component of the ore. And sometimes you get clays that will absorb a little gold. You can see that sometimes in column leach or in bottle roll leach tests where after several hours, sometimes the gold will actually fall out of solution. And I think that's because the clays are turning into gold absorbing clays. But in practice, you don't see that very much in heaps. I'd say the biggest thing about heap leaching is not enough thought is giving into building heaps as mills. And it's, of course, if you've heard me talk, I always say that there's a big difference between a heap leach and a dump leach. A dump leach is just a pile of rock that you get more out of than it costs you to build it. A heap leach is a mill. It should be designed to get a certain % recovery. The investors that invest money in your heap should reasonably expect that you're going to give them the % gold recovery or silver recovery or any kind of metal recovery at the rate you say you're going to give it to them and at the cost you say you're going to give it to them. But too many people sort of pay lip service to that and don't really build the heaps to do that. And once the heap leach is funded, people go out and they mine ore and they stack it in a relatively convenient way. And as long as it's performing more or less the way it's supposed to, everybody seems happy. I think we need to spend a lot more time designing those leaches and making sure that they're built the way they're designed. Certainly, the big push to me is good conveyor stacking. And I think a lot of work needs to be done on conveyors. I think top stacking of heaps is a wonderful way to go, but it is not applied that often. Normally you see a lot of retreat stacking of heaps. That works, but again, it's maybe doesn't work in an optimal fashion. So if we're going to carry the industry forward and we're going to really be proud of our industry, we have to make sure that we can target a recovery that we can achieve. And so people need to put more thought into this. They need to put, they need to look at the laboratory results and follow what the laboratory results say they should do. But then they need to do fairly sophisticated engineering. Heap leaching is sophisticated. It's not just us going out and piling up rock and saying, oh, look, gold's coming out the bottom or copper's coming out the bottom. That heap should be behaving internally the way we perceive it is supposed to. So that would be my comment. We need to take a little more technical approach to what we do. And it's working. There's about I think we got a number out of InfoMine the other day. It was like pulling hen's teeth to get it, but they said there's 600 operating heap leaches in the world. There's about 200 of those, or maybe 150 that are gold heap leaches. The rest are other heap leaches. So heap leaching is alive and well. We just got to make sure that it takes its place among proper processing techniques. Dual microphone.
There we go. Yes, I wanted to talk about internal ponding, and I think our future in heap leaching couldn't be significantly dimmed unless we understand and manage the ponds, the internal ponds that sporadic head inside of our heaps. Okay, now due to modern geophysics that's been developed over the last several years, we can actually look at profiles of solutions within our heaps. And the lower one is the project I work on in Mexico. And the lower one, we can actually see a large amount of solution that's trapped above the liner, which assumes pretty close to the brown line there. This not only represents a large amount of inventory of dissolved metals, but also a potential for catastrophic failure. Now, on the upper left portion, it shows a typical gravity drain that's been slowly utilized around in our industry. And so I wanted to discuss, and first of all, show that this practice and discuss during the later part whether this is really a good technology to try to recover some of the metals that haven't been reporting to our preg solution. If I can get the next slide to come up here. Here we are. Whoops. A little delay there. Looking at the geophysics of, the geostability of a heap, we know that when we have a solution buildup, there's two factors that maintain slope stability. Well, I'm not a real specialist in this area. I've observed that when you have a solution there, your friction factor goes to a minimum. It's like the difference between driving a car on a dry pavement versus during a rainstorm. When you go to put on the brakes, it's just not going to have the same friction factor. Well, this fluid in between the rock particles will add as a lubricant. And in addition, it'll add extra weight to the column of material above that plane. There's also cohesion between the different rocks. And when you lubricate that as well with solution, you're going to take that cohesion factor to a minimum. Now, the geostatisticians know exactly how to calculate this all out, but I wanted to point out that this is a natural physical phenomenon that exists in our heaps, and it's something that we must understand and manage. One of the first indicators that we have a buildup of head, or the bathtub effect, is we're going to get seeps on the side of the heap. And this is a real good indication we have some problems for solution flows. Either we're adding too much solution or we have a compaction layer that's underneath that needs to be addressed. This also can be accompanied by cracks along the crest or heap pad movement. This can result in failures for your side slopes. Now, this is not near much of an issue when you're dealing with valley fill, when your heap is pressed up against a mountain. But again, your crest, which face towards probably your process ponds, etc., that's where you have a potential for failure. And these failures can be catastrophic. There's a lot of rumors going around that several heaps have moved and some of them have failed over time. Now, we've had a lot of tails dam failures in the last 10 years, and Dirk can probably address that these really can hit the public press and give us a bad PR. So it's something we really must address and manage and understand. Okay, here's an example of a couple failures that have been on heaps that haven't been real large, but significant to cause spills, go over your liner, out of containment. There was one at Newmont back in the 90s when I was there that was very costly. we had some cyanide detoxification we had to perform, etc. But it didn't really hit the press very much, and it was managed very well. But it's something we want to avoid in future operations. Thank you.
Thanks, Thom. Next presentation, please. Okay, so I'm going to talk about closure. And, you know, this is not a laundry list. There's even more, but the big ones are, you know, what are the drainage rates over time? We know that obviously it's going to drain, and probably most of this, the high drainage rates will be gone within first year, and then it'll get down over the next 5 years into a lower asymptote that at some point will start to approach the net infiltration rate. What's the water quality over time? What's solution management? How are you going to handle that initial drain down? Do you need to treat for water? Do you need to treat for water quality? Are there potential impacts, surface water, groundwater, cover system design, slope stability, and erosion control? So, you know, Thom touched on this briefly already. There's run-of-mine heaps as well as crushed agglomerated heaps can be pretty complicated, and you get solution buildup. You get all types of heterogeneity between these systems. There's preferential flow, there's preferential airflow, there is stagnant flow where you have a solution that's captured in pores that are flowing very slowly, and they serve as a reservoir of water quality contaminants. So they're really complicated systems. And you know, in general, we need to be able to quantify those different components of the subsurface flow system. Matrix flow is going to control your residence time. In some of these big heaps, it can be hundreds and hundreds of years, and that's going to control the geochemistry. At the same time, you're going to have a lot of preferential flow, even in a crushed heap leach. It's going to flush out, and water quality is going to change at time. You have to be able to understand that if you're designing a water treatment plant. And depending upon what the material's like, it can change it in different ways. We've monitored outfalls on heap leach and waste rock dumps, and depending on what the material's like, you might see in the rainy season that the water quality concentrations will go down. Sometimes it will go up. So these are what I call novel subsurface systems. There's really nothing in nature like these systems, and so we have to think about that, and we have to keep advancing the tools to understand these subsurface systems. Cover systems, there's a lot of work that's been done on them. They are not a magic bullet. They will help control the infiltration into the waste, but all cover systems, water comes through them. And the other thing to keep in mind with heap leach facilities, they're already at a wetted phase, and they're at field capacity. So whatever goes in net filtration is going to very quickly come out. This is a graph from the Richmond Hill mine where they have about 20 years of monitoring data. And on the top of the graph is the precipitation rate by month. And the bottom of the graph is the flow rate. And then this little green line that you also see, that's some model output. And so every rainy season, and especially, every wet season, and it's primarily in the wintertime, there's a lot of snow. Springtime, you get this huge flush, and it's extremely rapid. You see a very rapid response within weeks from the snow melt on the outflow. And so in this particular area, what you can see is the flow rate early on is quite low, and that increases over time. So the cover system also changes. So you need to understand those types of things. And even though this was a low permeability barrier layer cover system, it's still leaking through at about 30% of the net infiltration rate. That's water that you have to deal with. Semi-arid climates, you might be able to get down to 1 to 5%. And what are the optimum cover systems, and what's the balance between water quality treatment? These are questions that every mine has to take a look at and go through a alternatives analysis and decide how to close these facilities. I just want to show this real quick. I already talked about this very rapid response. And in the modeling we did, basically we showed that it was 40% of the solution was the infiltration that was going through was coming out quite rapidly. You can associate that with preferential flow. The rest came out more slowly, matrix flow, stagnant flow, then contributing to the water quality as well. This is another study we did, and this looks at, I must have had something in there in the past. There's a phantom PowerPoint there, but it has a life of its own. But basically, this shows with a barrier layer that and this particular design is a barrier layer with a drainage layer and then topsoil vegetation layer. And on the y-axis is the net infiltration rate that's coming through. And so on the bottom axis is the hydraulic connectivity. And as you have a higher hydraulic connectivity, obviously much comes through. But what this basically shows is that even if you have a clay layer that's around 10 to the -6, there's still quite a bit. There's 10 to 15% of the precipitation that's coming through this cover system. And so if you want to use a natural barrier layers cover system, you have clay on site, you really need to get down in the neighborhood of 10 to the -7. Now, this is the climate from the Andes. It's quite wet, 1,500 millimeters of precipitation per year. Erosion control. It's the second biggest cost after water treatment enclosure. And again, it's got a life of mind of its own. So in this little graph here on the left, basically this is looking at the erosion from some topsoil material and whether or not you have no vegetation, which is the big column, all the way down to around 90% vegetation. And so in this particular climate, and what's interesting is most temperate and subtropical climates, the precipitation intensity or the IDF curves are not that great. They get a lot of rain, but they don't have monster 2-inch 1-hour storms like we do in Southwest in the United States. And so with those types, and here's an example, this is a mine in Peru as well, poorly vegetated, massive erosion. And, you know, unless you understand you've characterized your topsoil and you understand how to revegetate it properly, you're going to end up with big problems. Same site, there's other areas that are beautifully vegetated. Down at the bottom here, this is a semi-arid site. This is down by Tucson. This thing was on autoplay. Down by Tucson. So we had a cover system design where we put down a 30 centimeters of alluvium, and then we followed it with a rock armor because we knew the alluvium was highly erosive. Well, we saw how highly erosive it was. We had two 2-inch storm events within a couple of days of each other, massive erosion. And in these semi-arid climates, it's really the rock fragment that is controlling the erosion. It's not the vegetation. So don't think I just vegetate and it's going to take care of it. You have to consider the rock. And this little example right here, which we can't see anymore. We covered it with rock and now it looks like this. I took this picture about a month ago after 12 years. The plants are growing through the rock cover down into the alluvium and it's working beautifully. And it worked. We put rock up and there's been no erosion at all. And so this is a site where we just put no benches in, we leveled it out. So we have some slopes of 600 feet and it's a straight shot 3-to-1 and it's working beautifully. And then water management. Solution management closure. This is a big deal because you're going to get a big slug of water. How do you treat it? How do you reduce it? And then eventually in a semi-arid climate, you may be able to get it down to a low enough flow rate. You can send it to evaporation cell. How well the evaporation cell is going to work. What's the proper design? If you have a 15-foot deep evaporation cell, well, guess what? The bottom 5 to 10 feet are not evaporating. They're a holding pond. Okay. So these are the things that we need to consider. And so I'm just throwing that out there. And because these novel subsurface systems are so complex, you can sit there, you can run some samples in the lab, but you really need to get out there and monitor. You need to monitor what's happening in drain down. You need to be a monitor under operations and when things go, when you take things off, so you understand what's happening with the flow rate. You understand the water quality. Solution management, you need to plan for the worst. Okay, and specifically, I'm talking about water quality. I didn't mention PAG material, but there's a lot of heap leaches in gold that are running alkaline systems, but they have PAG in the rock, and over time that could go acid, and then you have an acid heap leach. you might as well be leaching copper at that point, because you have to deal then with the acid. There's a lot of unknowns. What's the long-term water quality? One of the big questions we're looking at right now is we're working on a site where they have a number of heap leach facilities, and they've all turned acid. And the question is, even though we put on a low permeability cover system, there's still massive amount of water that's going to need to be treated. So does it make sense to spend more money on a cover system, or do you just need to bite the bullet and treat forever? And we don't know what the long-term water quality is, because even though you might reduce the infiltration rate, the water quality could get worse because you're not flushing as much water through. These are unknown questions. Long-term cover system efficiency, you have changes in hydraulic properties, you have changes in vegetation, you have degradation from erosion. Ecotoxicology sooner or later is going to come, and they're going to take a closer look, and they're going to want to say, well, what's happening to the insects? Because the birds eat the insects. So we're not really interested just in the grass. We need to know what's going on with all your invertebrates. And then, of course, you know, the changes in primarily precipitation intensity that are associated with climate change, and how that might do with erosion and do with infiltration through the cover system.
Thanks, Mike. I have just a few comments about governance. And so this is more of a thought piece and maybe a bit of background to let us think about heap leach governance. I know that Freeport has a governance system established for heap leaching. I don't know the details of that. And so if anybody from Freeport want to share that, I would appreciate it. But I first want to talk a little bit about the failure of systems. If you have not read this book, Drifting to Failure by Sidney Dekker, is published in about 2012. It's very well worth reading, and it's worth rereading from time to time. It's well written. Dekker is a professor at Griffith University in Australia. He's also a certified Boeing 737 pilot. And so you'll see some of his writings actually coming up in some of the Boeing 737 MAX, as well as earlier Boeing and other crashes. He says there are 5 elements we've got to pay attention to when we look at the failure of systems. Constraints that impact the decision making. He says we've got 3 boundaries: economic, safety, workload. And if the economic pressure wins, it may result in borrowing from safety to accomplish the efficiency. And so let's be very careful of that. Second one is a series of small decisions can have a very large impact. These are small, unrelated decisions made by different groups at a site. Misunderstanding of interdependencies. System conditions that are interrelated can have high significant impacts on the outcome, but we need to understand how those interdependencies work. Models may be reliable. There can be unknowns that are not effectively evaluated due to incomplete information or other factors. And then the importance to look at the benefits from available governance and other systems. So really look at the measures and procedures must be identified and applied in the day-to-day approach to the management of complex systems. And he goes through all of this, and then he says, so what have we learned in our research? And he says, the key is diversity. Safety critical organizations are complex, adaptive systems. These organizations must pay attention to diversity. With diversity, a system had a large number of perspectives to view a problem with a large repertoire of possible outcomes. Plus, the diversity is not only diverse disciplines, but also diverse genders and all the diversity we have. And it struck me over the last day and a bit, just how interrelated things are in terms of heap leaching between metallurgical work and physical, what I would call physical engineering, stability, geotech, hydrogeology. These are closely related, and it's really diverse if you think about it. So if we go forward, we've got to look at what kind of failures could we get. To me, it looks like we clearly can get physical failures, which can lead to community impacts, environmental impacts, and Thom, you addressed some of that. But an economic failure is a failure in a heap leach. And so how would we address it? And so some ideas around diversity. I'm back at the ESG issue, Mark. I'm saying back at the ESG issue, environmental, community, social aspects, management and governance, very important. Design, construction, operation, and monitoring. We think we know how to do it, but we need to pay attention to the metallurgical material behavior as well as the physical material behavior. We have to look at emergency response and long-term recovery. And more, our communities expect disclosure and access to information. Now, you'll notice that the title says drawing on the GISTM. So I'm drawing here on the global industry standard on tailings management. Really, the issues that are highlighted in that standard are the issues here, which are the issues we've got to pay attention to. I'm sorry, but it will bring diversity. The places where we have the most difficulties are combining environmental, community, social, management and governance, and the engineering side. People would look at it as stovepipes, silos, but that integration is where the challenge is. And quite frankly, this is where I think we're all going to be as we move forward to the future of heap leaching. We're going to have to pay attention to all of these issues. And that's all I have.
Can we get some help from someone in the back to be able to hand a microphone to people who raise their hands?
We have enough microphones.
We have definitely enough up here. So questions? You have decades and decades of industry experience up here that's just waiting to answer your questions.
Hi, Mike, I'm going to ask you a question while we're waiting for other people. We've thought over the years about this idea of heaps going acidic, of gold heaps going acidic. And of course, people use humidity cells, which actually are not very good models of what happens in a heap after 10 or 15 years. Essentially, down inside a gold heap leach, there seems to be bacterial activity or whatever that turns all of the pyrite into acid. And a lot of heap leaches essentially have acid cores to them. And as you point out in closure, they almost all go acidic. So my question is, if you blend lime into those heaps, that's probably not a great idea because first of all, it raises the pH way too high to begin with. Secondly, it's expensive. And third, it's probably all gone after a few years. Have you run across gold heap leaches where people have intentionally blended limestone into their heaps?
I haven't, and I don't think that's a a bad idea though. And, you know, because the solubility of limestone is quite low, especially at high pH. We've worked on waste rock facilities and heap leach facilities at closure where, you know, we know that there's acid generation going on, but they're still remaining neutral. And you can see it from the sulfite TDS signature. And then going and looking at dumping records and seeing what the materials are, you realize, oh, well, you know, it's got a 1% sulfide, but it's got tons of calcium carbonate in it. So I think that's definitely a question that needs to be answered in the pre-feasibility and the feasibility stage is, you know, what is the long-term sulfide content of the material that's going to go in the heap? And if you're going to be leaching material that's got high sulfides in it, you probably should be adding limestone to save yourself a lot of headaches down the road in terms of water quality treatment.
Yeah, I'd like to respond to that. Back in the late 90s, on the Carlin Trend, we had a lot of potential bio-oxidation. And prior to building that, we did a lot of ore sampling, and we had some real high sulfite sulfurs in the 4 to 5% range. And we did columns, 6 month columns, to try to determine what the gold extraction over time was. And of course, we batched them in lime, and we did, I don't know, maybe 60, 100 of these columns. So I took a model and kind of compared what the chemistry was and the NCB model that Charles Buckman came up with, and determined a model on how much lime to add. And it was pretty copious amounts, and it was well mixed. And then the actual thing, there was a stockpile, I think it was a BLLS or something like that, in the north area that Barrick had and gave it to Newmont. And it was already producing acid rock drainage. And so we ended up crushing it and adding a lot of lime, according to what the NCB was, to the ore, often 10, 20 pounds per ton. And we had the operators that were taking sample a couple times a shift, doing a simple shake test after the lime was added, and then doing a pH. And then I put a graph together on how much additional lime they should add to the pH, et cetera. And to my knowledge, this has come down in pH in the 80s range, upper 8s, but they still haven't had an acid rock drainage problem from that heat. Oh, I also wanted to say it's in a ore control SME paper 2000. So if you look it up, Mr. Boland and I put together a paper on that.
Cool, thank you. My name's Sam. I'm a student in Missouri S&T, and we're working on developing new types of sensors for the mining industry, whether geotechnical or chemical. So I wanted to ask, you know, this experience panel, what areas of monitoring are we lacking in still that you would like to see improved, and what kind of attributes are you looking for that you know, a highly effective monitoring solution would have?
I just had a lunch with about 4 other people where we discussed that very thing with a group that's coming up with in-heap sensors. And I think the answer is that the approach is wrong if you say we're going to develop sensors and figure what to do with them. I think the approach should be, what are we going to do with the data we generate? And so the first question has to be, you have to talk to the mining people and say, all right, if you have this data, how does it help you? If you just know what's happening in a heap, but the mining people just build the next heap the same way, that's not accomplishing anything. So somehow the management, somehow you have to get to the management and say, okay, if we generate this data, how can you use this data? And then you can figure out what data to generate.
Yeah, I've got a few opinions on that as well. There's an unbelievable amount of sensors out there that have been developed for different applications. and there's a number of sensors that we use currently that are pretty successful. But the big challenge is really ruggedness. Okay, it's because a lot of these sensors, you just can't buy them off the shelf and stick them in a heap and expect them to survive. And then how do you install them so that they're not damaged during the installation process? And you're dealing with millions of tons of ore that may be out there, and you're taking point measurements from sensors. So it really also becomes the question of how do we sample at a high enough frequency, both spatially and temporally, that makes any sense that, as Dan mentioned, you can use. Okay, so there's a number of sensors I'd love to use out, like, you know, a nice, find an ORP sensor that you can bury, but you know, you're talking $1,200 for an ORP sensor. Now, if someone comes up with something that's $200, then it starts making a lot more economic sense, because you know, at $1,200 sensors, you can only stick a number of sensors out there, and you have a tiny little window on a huge landscape. So they need to be cheap. They need to be very rugged to deal with mining.
Ideally, you have to put so many in that you can get a 3D effect. So the first thing the sensor must do is to figure out where it is, because you're going to have settlement. And so whatever you do, you've got to start with a sensor that can find out X, Y, Z. Sorry, I was in Canada too long. Yeah, so that's a key. The other thing is, don't connect the sensors with wires. They've got to talk to each other. So you've got to have a battery system that's strong enough to talk long enough. How long? 5 years, 6 years, 7 years. So those are, I think, some of the underlying parameters. I mean, if you have sensors that can do moisture content, that can get an idea on flow, so it's not only water content, but potentially also fresh flow, so it may be a change in temperature. You know, there's a lot of those that can go into tailings. You just spray them out all over the place, and you've got a three-dimensional framework. They've got to talk to each other, and then they've got a feedback so that you can actually have that right in your computer. It's a huge task. There's a university in the University of Chile in Santiago as a group that's also been working on sensors, and I'm sure you guys are in contact with them as well. Other questions?
Okay, I'm going to jump in and change the subject here. I'm going to attack Dirk for a minute. We all pay lip service to ESG, and all of us guys up here on the stage are old enough that we can just pay lip service to it and ignore it. But if the industry is going to continue, people have to do more than just that. My problem with ESG is how you implement it. If you say, okay, you guys, you need to pay attention to what other people are thinking. And so you then form a big group of people that get in the same room, and you've got a bunch of native people sitting on one side and a bunch of us mining engineers on the other, and a bunch of economists and businessmen and politicians in the same room. They all talk to each other, and then they go away, and nobody's actually listened to each other. So I think what needs to be done if ESG is going to get implemented is there needs to be another layer put into this whole process, where obviously if you get people who are living in a village in Guatemala, which is one place I'm familiar with, talking to a bunch of mining engineers from North America, there's not a lot of intelligent information being absorbed by either side. So I think what we need to do is say, if ESG is going to work, there needs to be an intermediate layer. There needs to be a group of sort of intermediate people and I'm not sure who those people are, that could say, talk to the villagers in Guatemala. And then the engineers can talk to this another intermediate person, and those intermediate people maybe listen to each other. And maybe the thing works a lot better.
Yeah, no, Dan, you're right. There are many ways of doing this. I recall, I've got his name now, but a guy that did a lot of exploration work in Bolivia and all over the place. And he said, the only way you're going to reach the community is you're going to have to go stand in the kitchen and drink coffee. Doesn't matter whether it's in Nevada, whether it's in Bolivia, wherever it is, that's what you have to do. Was recently at Yanacocha. We had a presentation by the person that handles the social issues. They have a lot of communities they deal with, and they've had issues in the past. And so I said to him, so how many people do you have? He said, well, let me count it. It's the people working with me. We have an NGO that we support. We have a foundation that we support. It's about 78. Okay. Was in Ghana at a mine. Also with issues, saying, how many people do you have? 23. Now, I'm not going to ask any of you how many people you have dealing with social issues around your mine, around your heap leach. You cannot do it by inviting people to a meeting room. In Canada, when you do that, you may have to pay people to come to the meeting. That's part of the culture. And so you really need to reach out to people. You've got to build trust. Once you get to the point where they trust you sufficiently, and there are many examples out there, you keep working, and finally you will get to the place where, first of all, you've got to be accepted. Second one is you've got to build trust. And finally, you get to the place where you become partners. You come into a hotel at the community, and the lady in the hotel says, welcome here. Glad you can come visit our mine, not the mine, our mine. So they're great examples of how people do this stuff. Mark and some of his colleagues will present a paper later this afternoon, also on this capacity building piece, this is very hard work. It's not stuff that I can do as an engineer. We have to deal with people in the social end of the spectrum, and there's some very, very good people out there. There was a lady handling social issues many years ago with Newmont, and that was an Australian lady, and we were talking about how do you handle social issues, and I said to her, so tell me about the issues you deal with. She said, the biggest enemy of dealing with communities is engineering schedules. She says, because I would get a call from a project manager that says, I need to build the mine. We will start construction in 8 months. And we have problem with the communities. She said, I can't do anything in 8 months. I'm going to need years. And so this is, I think it's a learning thing for all of us. It's hard work. It's extremely hard work.
Well, also maybe the time frame needs to work backwards too. I think that what we're all seeing is that mines are taking longer and longer and longer to put in production, and that's going to seriously damage the social fabric of the world. So it's not just enough to say engineers should accept the fact that it takes 10 or 15 years to build a mine. Maybe somebody needs to talk to the other side and say, Okay, it has in the past taken traditionally 10 years to build trust with you guys. How do we do that in 2 years?
At the risk of already talking too long this morning, but I've had the pleasure of doing a bunch of mines all over the world. Some for Newmont, some for industrial minerals companies prior to Newmont, some for my own self. And social trust is not something you're ever given. That's number one. And we had a great man in Newmont called Lynn Harris that I had the pleasure of working very closely with on a number of operations, Africa and South America and so on. You have to earn that trust. And I think that goes to the comment about having coffee in the kitchen, if you will. Whether that kitchen happens to be the governor's office or the president's office or wherever that kitchen is, it makes no difference. But you have to earn that trust. When we went into, I'd left Nevada in 91. And the Nevada I knew when I returned, that I had known in 91 when I returned in 2010 from being other places, was not the Nevada that I left. I would argue we had lost a lot of trust. I was very unhappy with that. And I think we didn't maintain that daily, almost hourly communication and interaction with our publics. And really, to me, that's what it takes. You talk about numbers of people, it's not numbers of people. I would argue, I'll go back to that damn little mine called Pan that I talked about this morning. I had 52 or 3 people of ours on our payroll, another 50 or so contract miners. Every one of those people was an ambassador for that operation. And you gave those people the information that they needed. And really it was trust in yourself, in that management team, that you're going to be doing the right things. And what are those things? Because we don't know what those are as one individual. We have to have that input from everybody on that team. And that's not easy. It takes a lot of work. Then we have the attribute that we have to make money if you're going to be a company. This goes to how can you do something in 2 years? You cannot. You've got to have a reputation that you've taken to those locations that you can point to that you've had in place for a number of years. So it's not a simple dynamic that you walk in, here's the recipe, here's how you do it. You have, in my view, you have had to walk the walk as well as talk the talk. I think, candidly, I'll use Newmont's name. I think they've done a good job over the years of that. When they go into a community, it's different than Ken Brunk as a junior miner on a Toronto Stock Exchange. That already has a stigma, and it's not a positive. We have to work with it. If you have that other company, the Newmont, they have a different, because they've earned it. They have a different reception. So anyway, I think it's a situation of establishing a practice and walking the walk and showing that you mean it. And until you do that, and until we do that as an entire industry, we're going to be where we're at. And I've seen it for the last 60 plus years. Are we better? You're damn right. We are technically better. I'm not sure we're socially a lot better. If you go back and read De Re Metallica, we had the same problems then that we have today. Does that mean it's doomed? No. Get smarter, guys. Damn it, you've got decades to do a lot better than we've done. And get integrated. Thank you.
Hi. So in northern Nevada, we do notice a lot of carbonaceous ore around. And fortunately, Nevada Gold Mines has the roasters to treat those. For the heap leach mines, once you get into carbonaceous ore, it becomes a problem. So what would be your advice to the heap leach mines on how to deal with the carbonaceous ore so they can be ahead of those particular ore bodies?
Well, there's maybe two categories of carbonaceous ore. The one that's black and ugly, it's fairly easy to take care of. You just avoid it. There's also carbonaceous ores or preg robbing ores that aren't necessarily black and ugly. A lot of the organic components in an ore are left over from whatever happened to live when the limestone was deposited. And that stuff hasn't necessarily turned into black carbon. It's very various organic compounds. So the answer is there is no answer in the heap leach itself. You should certainly run column tests in advance to determine how much preg robbing there is in your ore. And I think we tend to maybe miss the boat in that, say you have a heap and say the heap runs, let's call it 2 grams of gold per ton. The solution coming out of the heap might run 2 grams per ton on the average. But the first solution coming out of an operating lift probably runs 6 or 7 grams per ton. So if you suspect carbonaceous components in your ore, you should be testing those for preg robbing at 6 or 7 grams per ton. So I think those, but there's nothing really you can do. I don't know of anybody that has come up with a way to make preg robbing ores not preg robbing in a heap leach situation.
Okay, I think we should probably wrap up. We have time for one more question.
I'd like to comment on that last one. We've observed that when the pH drops somewhat in the heaps and you have calcium sulfate present, it'll co-precipitate some of your preg solution. But if you raise the pH back up and add additional cyanide, free cyanide, you'll be able to remobilize that. So sometimes it's just a matter of getting your reagents in proper ranges. Thank you.
Okay. Any other questions? Last one.
So a quick one. I know we've talked about copper, gold, nickel, really briefly talked about vanadium, uranium yesterday. I know that's a real small part of the periodic table. So what else is on the horizon for heap leaching?
You're gonna ask the geotechnical engineer to answer that question. I mentioned briefly before, I've seen iodine, and nitrate heaps. I don't see a particularly good reason not to heap leach lithium. And in Chile, it's the same people mining the lithium, the big lithium deposits that have experimented with both nitrate and iodine leaching. We're seeing pretty complex polymetallic leaching in Finland, where they're getting zinc and among other minerals. So, anything for which there's a cheap solvent, I think is a candidate for heap leaching.
Our colleagues at West Virginia University got some funding from, I believe, the Department of Energy to look at basically heap leaching coal waste for rare earths. And so that's another piece that seems to be on the horizon as well. Can I make a quick announcement about tomorrow? Go ahead.
Yeah, I'd like to add also that when I was working as a process metallurgist, rarely did I look at process solutions for other than the valuable metal that we were looking at. And I just want to suggest, if your process solution sometime, maybe once a month or once a year, get it analyzed for critical and strategic elements as well as rare earths. You never know what's going to show up in your process solution that you didn't anticipate, and that might be something of value.
Yeah, and an example of that is that Freeport built a rhenium plant down at Sarita, and it's been very profitable for them. And it was there; it's always been there, and so now they're making money on it.
Thanks.
You're done.
I'm done.
Okay.
Okay.
we're done.
I just want to talk a little bit about the schedule tomorrow afternoon. We will most probably end the session at 2:30, 2:45 timeframe. And the other day, Dan invited, during the short course, Dan invited people to come visit his lab tomorrow afternoon. Those of you who are free, you can visit Kappes Cassidy lab. I talked to Jack McPartland of McClelland Labs. They will also be open, and people are very welcome to go and visit any of these labs tomorrow afternoon. We don't have any transportation organized, but that would be on your own shoulders at this point. So please take advantage of that. You also have received emails about tonight's buses to Mackey and back. And so we look forward to seeing you tonight on the bus and also over there. Thanks.